To illustrate the concept of acid-base titrations, we're going to use problem 4.85 from your textbook. In this problem, a quantity of 18.68 milliliters of KOH solution is needed to neutralize 0.4218 grams of KHP, which stands for potassium hydrogen phthalate. From that information, you're supposed to determine what is the concentration in molarity of the KOH solution. So potassium hydroxide, as you know, is a strong base. KHP you might be less familiar with. KHP stands for potassium hydrogen phthalate. Okay, so it's important to remember, especially later when we calculate the molar mass for KHP, that the KHP does not stand for potassium hydrogen phosphorus, which is a pretty common mistake that students make. It's an abbreviation for potassium hydrogen phthalate, which the chemical formula is KHC8H4O4. This is a salt, and so when we add potassium hydrogen phthalate to water to make an aqueous solution, the potassium and the hydrogen phthalate separate and dissociate into free ions, potassium ion and hydrogen phthalate anion. The hydrogen of this hydrogen phthalate is acidic, and so in a reaction with a base, in this case sodium hydroxide or potassium hydroxide, in this case it's potassium hydroxide, the hydroxide reacts with the hydrogen phthalate. The hydrogen phthalate donates its hydrogen as a H plus to OH, the OH minus, to produce water and also phthalate anion, which has a 2 minus charge. This is the equation describing the reaction that's going on for the particular titration that we're doing in this problem. It's a reaction between hydrogen phthalate, an acid, and the hydroxide base to form water and phthalate anion. Now, most titrations are done using a burette. So let's just do a quick diagram of what this will look like. This is a rough sketch of a burette. We'll fill this with our potassium hydroxide. So there's the potassium hydroxide in blue. Then we'll take a flask. So I'll do a rough drawing of a flask, and we'll put in that the dry potassium hydrogen phthalate. So we're putting in the salt, the dry salt. That's what we've weighed out for the problem, and the problem says we have 0.4218 grams of that salt that's in the bottom. Usually then you'll take that salt and we'll add water to it to get it dissolved in a solution. Okay, so now we have a solution of potassium hydrogen phthalate, and of course in that solution we had 0.4218 grams of the compound. What we're going to do now is titrate the potassium hydroxide drop by drop into the potassium hydrogen phthalate until the end of the titration is reached, until the end of the reaction. And we'll know that happens because we're going to add an indicator to the solution. And usually for these types of acid-base reactions, the indicator is a compound called phenolphthalein. Phenolphthalein is colorless in the acidic KHP solution, but then will turn pink when you're just past the end of the reaction and there's just a slight excess of hydroxide. So let's start putting in the potassium hydroxide. So notice I'm adding in potassium hydroxide to the solution, and now watch, it turns pink. So now we know to stop adding potassium hydroxide because a pink color has appeared, and so I'm going to stop adding any more volume of potassium hydroxide because I've reached the end of our titration. Now we should make a note about the difference between equivalence point and end point. The equivalence point of the titration is when the moles of hydroxide are equal to moles of KHP in this case, because we have a 1-to-1 ratio in our balanced equation of the hydrogen phthalate to the hydroxide. And this is called the equivalence point. However, the pink color doesn't appear until we have just a slight excess of hydroxide. So when the solution turns basic, then the phenolphthalein turns pink. And so we need to have just a slight excess of base, and that occurs just after the equivalence point. So we've reacted exactly the amount of hydroxide with KHP to reach the equivalence point, but to actually observe the end point, to know when the reaction is ended, we add just an extra drop of hydroxide, and that is called that is the indicator of the end of the titration, which is called the end point. So at the end point, we see the pink color. Now, if we've done our titration very carefully, then our end point should be a really close approximation of the equivalence point of the titration. In this case, our end point, when the pink color appears, occurs at 18.68 milliliters of potassium hydroxide solution added to the KHP. So how are we going to do this calculation? Well, we're looking for molarity, moles per liter of the KOH. We have a volume of KOH, but we don't know how many moles are in that particular volume, that 18.68 milliliters. So how can we get the moles of KOH? Well, we know how much KHP we have, 0.4218 grams of KHP. And if we can calculate the moles of KHP, then based on our mole-mole ratio, right, of 1 to 1, we should be able to calculate the moles of hydroxide that were in that 18.68 milliliters. And then using that number of moles and the volume, we can calculate the concentration. So we're going to go from mass of KHP to moles of KHP, and then using the balanced equation, the moles of KOH, calculate that, and then finally to the concentration of KOH by dividing the number of moles by the volume that was titrated. So to do this calculation, we're going to need first the molar mass of KHP. Since we added the whole solid, the potassium hydrogen phthalate, to the flask, the dry salt, the molar mass of that is 204.2 grams per mole. And using that, we should be able to calculate the number of moles of KHP. So moles KHP is 0.4218 grams, and then times the inverse of the molar mass, so 1 mole over 204.2 grams. It's the inverse, so that grams will cancel, and that gives us 2.065 times 10 to the minus 3 moles of KHP. Now, since it's a 1 to 1 ratio in our balanced equation of moles of KHP to hydroxide, that means that our moles of hydroxide is going to be equal to the moles of KHP that in the flask. So 1 to 1 ratio, and just for thoroughness, we're going to just show this. So we have 2.065 times 10 to the minus 3 moles of hydroxide. Since the KOH, the potassium hydroxide, has 1 hydroxide anion in the salt, the moles of hydroxide is also equivalent to the moles of KOH. Now we can get the concentration of the KOH in molarity, moles per liter, by taking the 2.065 times 10 to the minus 3 moles, dividing by the volume, and it's important to remember we're dividing by volume in liters. The volume was given to us in milliliters. We'll convert that to liters, so it's 0.01868 liters, and that ends up being 0.1106 moles per liter, so 0.1106 molarity potassium hydroxide solution.